So when we fabricated the 2D complementary devices, we understood the general principle in the turn-on condition of source-gated 2D FETs. But we didn't stop with the general picture, but proceeded with studying the threshold condition in more detail. So to understand the physical mechanism that causes the turn-on condition of 2D FETs, we need to first understand why the conventional threshold voltage definition and model are not applicable to source-gated 2D FETs. So for thin-film body MOSFETs with near-intrinsic bodies, many parameters affect its threshold voltage. But the physical mechanism behind this turn-on condition is based on achieving a critical surface concentration in the channel. This is in the order of 10 to the power 16, and this translates to about 0.35 volt, which is needed to be applied in the gate. For 2D FETs, on the other hand, even the source drain metal affects the threshold voltage, suggesting that the physical mechanism for the turn-on condition is different. And this requires us to incorporate the barrier height at the metal 2D junction into the model, and by extension, the widely observed Fermi level pinning effect. So, what is the condition for the threshold then? So, to determine the condition for threshold in 2D FETs, the current conduction path must be first identified. As I mentioned earlier, there were two trajectories which are reported to describe how carriers are injected into the channel, either aerial or near edge. So to determine the real current path for a source-gated 2D FET, where the maximum current density from the drain to the source occurs must be known. And this can be identified by tracing the maximum current density from a 2D contour and vector current density plots when the gate voltage is set to a high value and the drain voltage is set to a low value. So it should be noted that in our simulations, the thickness of the 2D film is selected, but considering a thickness where quantum confinement can be ignored. So, which is when there are at least 5 layers of 2D material films, but still thin enough for carriers to tunnel through. So to focus on the turn-on condition and ignore any short channel effects, a 1 micrometer channel length is considered. So should be noted that in our TCAD simulations, the representative 2D film used is MOS2, and a barrier height of 0.3 electron volt is assumed, which is within the range of the barrier height at the metal MOS2 junction extracted in experiments. So when the maximum current density is traced, the real current path when the device is on can be approximated to be near the edges of the contacts and at the surface of the channel, which is represented by the vertical line segment from A to B and the horizontal line segment from B to C. So we can then extract the conduction band profile along this approximated current conduction path. So we can do this at different gate biasing conditions. So when the applied gate voltage is equivalent to the gate to source work function difference, which is represented here as VG1, the band diagram at the gated source region and the channel are flat. And the surface potential at the 2D dielectric interface, which is at point B, represented here as phi is 1, is basically 0. So as Vg increases, say to Vg2, negative charges are then formed in the source and in the channel. So this comes from electrons that are thermally emitted from the source. So when the conduction band edge at the channel aligns with the quasi-Fermi level of electrons at the source, which is represented here by Vg3, electrons can start to tunnel from the source to the channel, and they encounter two barriers in the process. So the 2D film thickness and the source channel transition region, which is highlighted in gray. So as Vg increases even further, the source channel transition region completely disappears, and the surface potential at the 2D dielectric interface at point B becomes equivalent to the barrier height at the metal 2D junction. So now, what do these boundary conditions entail in the IDVG curve? So to explain their implications, we first determine the different current components using classical equations. So we can see here that at VG2, the device still remains off and the main contact transport is via thermionic emission. At VG3, the current becomes dominated by tunneling, mainly through the direct tunneling mechanism. So beyond VG3, there is still a steep increase in current corresponding to the disappearance of the source channel transition region. So when VG4 is reached, the main contact transport now becomes dominated by tunneling through a triangular barrier, or most commonly known as FN tunneling. And a gradual increase in the current can be observed because the barrier narrowing now occurs along the 2D film thickness. So, given these correlations between the band diagram and the transfer curve, it becomes clear that the turn-on condition happens when the applied gate voltage induces a source surface potential equivalent to the barrier height at the metal 2D interface. And the charges in the channel will mainly come from electrons that tunnel through using FN tunneling. So after identifying the onset of tunneling, we then need to solve for the surface potential at the gated source region phi-S1 to derive a closed-form solution for the threshold voltage model. So using Poisson's equation, integrating it once, and using appropriate boundary conditions, we can then solve for phi-S1 before the threshold condition is reached and across different gate voltages, where the model could match the simulation results closely even when different source metalwork functions are basically used. So for most 2D FET demonstrations, the gate is designed to overlap the entire contact length. However, the end goal is for the gate to be redesigned in the future so that it will have almost no overlap with the contact regions. So we need to know how the overlap affects the threshold condition as well. So to do this, we must determine how the gate and source fringing fields affect phi-S1. And this can be done using conformal mapping. So the gated source region can be basically divided into two parts. So we have the overlap region and the underlap region. So the oxide and 2D film overlap capacitances can be then solved by treating the overlap region as parallel plate capacitors, while the oxide and 2D film fringing capacitances are estimated by mapping the perpendicular surfaces into an equivalent parallel plate system using conformal mapping. So the overlap and underlap capacitances are then summed together to obtain the effective oxide and 2D film capacitances. So using straightforward derivation, the implicit expression for phi-S1 is then modified to incorporate the effect of the gate overlap, and a close matching between the model and simulations is achieved. So now that phi-S1 is captured and the effect of the gate overlap is incorporated, a closed-form solution for the threshold voltage for 2D FETs with a doped body and gated source can be then expressed as follows. And this is again based on the criterion that VT is achieved when phi-S1 becomes equivalent to the barrier height at the metal 2D interface, which we call here as phi-SBH. So from the given expression, the dependence of the threshold voltage to the barrier height at the metal 2D junction and the device geometry become more apparent. So when the barrier height formed at the metal 2D junction is high, the threshold voltage is also large because a high gate voltage is needed to promote tunneling at the gated source. So when the oxide thickness is scaled down, the gate has more control over phi-S1, so thereby requiring a small gate voltage to turn on the device. So the opposite is true when the 2D film thickness is reduced because the electric field at the metal 2D junction will dominate at thinner films. So when the gate overlap length is reduced, a larger gate voltage is needed to control phi-S1, thereby increasing the threshold voltage. So while our model could predict the barrier height and geometry dependence of VT, this is still within the simulation domain. But in actuality, fabricated devices experience a Fermi level pinning effect at their contacts, and this is brought about by interface states at the metal 2D junction. So the next question will be how to incorporate the Fermi level pinning effect. So let's take the experimental results for 2D FETs based on MOS2 as an example. So for MOS2, as the charge neutrality level of defect states occurs near its conduction band edge, the metal Fermi level typically aligns near the conduction band edge of MOS2 regardless of which kind of metal is used, whether it's a low work function metal or a high work function metal. So when the contact metal work function used lies within the band gap of MOS2, the effective barrier height is still a function of the difference between the metal work function and electron affinity of MOS2. But this is with a certain proportionality constant. So this proportionality constant is what we call the pinning factor, and it is represented here as X. And this pinning factor is 0 when the barrier height is completely independent of the metal work function. So for MOS2, the typical pinning factor observed is around 0.1. So when a lower function metal is used, aligning above the conduction band edge of MOS2, the pinning factor becomes unimportant as there is a high density of electrons, and the transition on the effective pinning factor as a function of metal work function is exponential as governed by Fermi-Dirac distributions. So to incorporate the Fermi level pinning effect, we therefore need an effective barrier height and pinning factor or S parameter that are consistent with the physical picture I just explained. And they are expressed using the following expressions. So after solving for the effective barrier height due to Fermi level pinning effect, and also incorporating an effective interface charge term, so to be able to account for non-idealities in the oxide during the fabrication process, the threshold voltage model is then modified, and the threshold voltage extracted from experiments is well now within our prediction or is well captured by our model.